All right, so now we are going to introduce regularization. Right? So what is regularization? So recall that we already saw this bias variance trade-off, right? So in tutorial 1 and in lecture 3, the expected error of our model can be expressed as the sum of three terms of variance, bias, and, well, the irreducible error, so variance of this random node. The core idea of regularization is to consciously introduce some amount of bias, so that this bias goes up, at the same time reducing the variance, right? So basically, if we have a model that is too complex, and if it is too complex and too flexible, we kind of penalize it for being too complex. And by penalizing it, we consciously reducing the bias, increasing the bias, but reducing the variance. So this can be done by modifying the loss function. So recall that the loss function for linear regression is this mean squared error. Well, we actually do not have to have this 1 over n. So instead, we can use the just the total square error, or the residual sum of squares. Ridge regression, or it is also called Tikhonov regularization. Yeah, so Tikhonov originally invented it for some other problems, but when people used it in statistics, they called it ridge regression. Well, in any case, so this is changing the loss function by adding a new term. So this new term is the regularization term, and it kind of penalizes the model for being too complex, right? So basically, the idea here is that if the coefficients of the models, well, at least one of the coefficients is too large, beta, then the model is going to suffer from penalty, right? So, and instead of using the original loss function, we're going to use the loss function in this modified term with this one extra term. So notice important thing that beta 0, the bias, or the constant coefficient, so the beta 0 or the intercept is not here. The reason it is not here is because basically beta 0 can be, it is just the expected, it's supposed to be just the expectation of our model, or the, I don't know, is the mean observed outcome. So it cannot really be too complex. So, which is why we do not include it. So the training this model means minimizing the loss function. So just like when we train a linear regression, we minimize the loss function for the linear regression. When we train a ridge regression, we minimize its modified loss function. So let me explain how we can derive the modified loss function, the gradient of the modified loss function. And so, so first, let me write down the partial derivative with respect to beta 0. So since beta 0 does not appear, so note that beta 0 does not appear in this extra term. So which means that the partial derivative with respect to beta 0 is going to be just the same as that for the linear regression, right? So it is going to be just minus the sum from 1 to n of 2 times yi minus beta 0 minus the sum by j from 1 to p of beta j x I j. Right? Okay, so how about the derivative with respect to some other beta j? So basically, we're going to have the same term as here, from 1 to n, 2 times yi minus beta 0 minus the sum from j equals 1 to p beta j x I j. But now it is going to be multiplied by xij, right? Because when we differentiate with respect to beta j, we've got to multiply by the partial derivative of this thing, so which is going to be xij. So times xij. But now we have this regularization term, and it does contain our beta j, right? So we've got to add plus 2 lambda beta j. All right? Okay, cool. So now we are going to just combine these together into a matrix form, right? So if we form the vector dl d beta 0, dl d beta 1, and so on, right? So this vector dl d beta 0, dl d beta 1, and so on up to dl d beta p, we're going to get this, as you can hopefully easily check. So minus 2 times x. X is the whole matrix of our training data. X transposed times y is our observed outcome of y, minus x beta plus 2 lambda beta. Well, this one without beta 0. Yeah. Okay. So now, in order to find the minimum value, we are going to equate this to 0, right? So we will equate this to 0. And, well, so how can we solve it now? So when equating this to 0, so basically 2 is going to cancel out. So we are going to have minus x transpose y plus x transpose x beta. And so plus lambda beta should be equal to 0. Well, but this is the same thing as moving this minus x transpose y to the left-hand side. So x transpose y. So taking out beta, we are going to get what, x transpose x plus the identity matrix times beta equals x transpose y. So our optimal beta is going to be x transpose x plus I inverse times x transpose y. Well, the main point here is that we can just directly derive it from solve it explicitly in closed form. Right. So here is our new loss function in the matrix form. Right. So here is the solution that I just derived. So yeah, know that it depends on the parameter lambda. So if we choose a different value for lambda, then the outcome is going to be different. Now, in the tutorial, we're going to find the expectation of this beta hat. So, and see that there is a bias here, right? So it is the original beta that comes from linear regression plus some bias. And here is, this is the bias. And here is the variance of beta. And again, so if you think a little bit about it, you will see that the variance is decreasing. So if with lambda. So because basically there is a division by lambda. That's the idea. Okay, now in order to see how it works in practice, we are going to use this credit data set, but since I wanted to plot coefficients at different variables in the credit data set, I'm going to standardize it, right? So basically, I'm going to replace every variable, well, every numeric variable here, x, with its own mean. So x minus x, its own mean, divided by the standard deviation of x, so that the outcome has 0 mean and standard deviation 1. This is needed so that we can directly compare the coefficient at, say, education and income. So because otherwise it doesn't make sense to compare them. And here is the outcome, right? So what I did here, I plotted, so I fitted my ridge regression for a lot of different values of lambda. For every value of lambda, I found some coefficients, right? So what this is, so for a specific value of lambda, these numbers here, so they're estimates for my coefficient. So essentially, this is my beta hat. And we can see that, when lambda changes from small to large number, these coefficients, they become smaller and smaller. So which is why it is called a shrinkage method. And this is very reasonable. This is what we expect to find. So what is the best value of lambda in the ridge regression? So we can just do it by cross-validation. Right? So we can try all different values of lambda. For every one of them, we find the cross-validation error, and then we just pick the value of lambda that minimizes it. So in this case, this is the value of lambda. So this is some sample of coefficients of ridge regression. So notice that if lambda is large, then the coefficients become extremely small. Well, minus 37 essentially means that it's almost 0. But so if lambda is, well, not so large, so the coefficients are kind of small. They're not exactly 0, but they're kind of small. And the bigger lambda is, the bigger these coefficients become. Okay, so this is the end of part 5. So please do the quiz now.